Hello everyone, myself Deepa Singh, working as assistant professor in Gyan Vihar School of Pharmacy, SGVU. Today we discuss about distribution, means how kinetic is responsible or how kinetic play important role for drug distribution, certain reaction required for this kinetic and significance of drug distribution. And this topic is biopharmaceutical and pharmacokinetic subject of 6th semester. So before starting this topic, you should know about some basic objects, and this basic object mainly you should include short introduction about distribution of the drug, and just to you overview what are the distribution, definition of distribution, and description about the distribution, because in previous slide we already covered introduction part of the distribution, and in this you just know all the parameters required for distribution and what is distribution, introduction of a kinetic required for drug distribution, which kinetic is required for drug distribution, and different reaction for kinetic of this drug distribution. Next is significance of drug distribution, and this majorly cover different significance for drug distribution or how this significance play important role for this distribution. So all this you know about in this topic. In the introduction part just we covered a short description about this distribution. And once a drug has gained access to the bloodstream, the drug is subjected to a number of processes, and the process is called as deposition process. Means when drug is entering the blood or after that, when the drug is subjected to reaches in a bloodstream or blood circulation, the process is mainly known as the deposition process. And in this deposition process, wherever the plasma level concentration means drug reaches in your plasma in deposition process, and this deposition is further divided into two parts, that is distribution and elimination. And you know all these parameters, what is deposition process and what is distribution and elimination. Means deposition is again further divided into two parts, and distribution is a part of deposition process, and distribution is that the which involve reversible transfer of the drug between the compartment. Means in distribution mainly reversible processes takes place, and reversible transfer of the drug takes place from one compartment to another compartment, or maybe blood circulation to site of action in a reversible way. And then in this distribution, no excretion or no elimination takes place. And next is elimination. Elimination means which involve irreversible loss of the drug from the body. Elimination may be subdivided into two parts, that is metabolism and excretion. Means excretion and metabolism is the part of elimination, and irreversible process is observed in elimination, and it compromises the biotransformation and excretion both process, but it just opposite to distribution. Means you can see that deposition is divided into part, one is distribution, second is elimination, but distribution is reversible process and elimination is irreversible process. This loss of the drug takes place from the body by the biotransformation or by the excretion. Next, in drug distribution, refer to reversible transfer of the drug between the blood and the extravascular fluid and tissue of the body. Means in this mainly to say that distribution is reversible process from one compartment to another compartment, and this reversible process is the transfer of drug from blood to any other extravascular tissue or extravascular fluid to the body. And there is some example of extravascular fluid and tissues like fat, muscle, and brain tissue are the example of this distribution process from one compartment to another compartment. And in this distribution is a passive process for which driving force is the concentration gradient between the blood and extravascular tissue. And you can say that distribution is also as a passive process or passive mechanism, because in this mechanism part of the transport or mechanism process, we say that passive diffusion is no energy is required, and this is a concentration gradient process. So in distribution, this distribution part is a passive process, because in this driving force is a concentration gradient, and blood flow and extravascular tissue, which is this passive process, and driving force is mainly concentration gradient between the blood and extravascular tissue. And this the process occurs by the diffusion of a free drug until equilibrium is achieved. Means in distribution, the transport of a drug from one compartment to another compartment is continued until the equilibrium is reached released or completely drug is passes from one compartment to another compartment or saturation is achieved until this process takes place. So it is also known as reversible process. And as the pharmacological action of the drug depend upon its concentration and at site of action, distribution plays significant role in the onset, intensity, and duration of action. Means if you see there's a pharmacological action or distribution, how it play important role for pharmacological action. In this concentration at the site of action means a desired site or at particular site where action is required. This is mainly depend on the distribution of the drug, how much drug distributed to that particular site. And this is also important for onset of the action or intensity of the drug or duration of the action. Means how much time or how much time is required for a particular drug. Or suppose you prepare control with this tablet. In this condition, ensure that your drug is being in a slow manner or not, and a particular duration is desired or not for your formulation. So this pharmacological response is observed in distribution, and it is also so significant role in not only for distribution but also onset of action, intensity of a drug, and duration of the action. And next is distribution of a drug is not uniform throughout the body because different tissue receive the drug from plasma at different rate and different extent. In previous lecture, we already discussed about plasma protein and plasma protein binding of the certain intracellular, extracellular blood tissue and the site, how it gets bind or the affinity, which sites are available for binding. And in this previous slide, we also observed that not every tissue have a similar affinity or similar capacity for binding, or binding site is also not available for all drugs are same. So this distribution is also depend on where the drug is present or which site is show that particular effect, or body tissue which receive the drug, how much drug receive that particular tissue or organ, or how in different extent it show the effect. So this distribution is not showing particular desired therapeutic effect, but this is depend on all the parameter, how drug is passes in your body or which site it reaches or which amount of drug extent present in your body, that particular site. All these parameters are important for this onset of action or showing therapeutic response. In this, we can say that the next part, volume of distribution. Volume of distribution also we discussed shortly in previous slide. It is also known as ED. Volume of distribution with XY amount of drug present in your body divided by amount of drug present in your plasma. And the volume of distribution of BD is also known as apparent volume of distribution. Means another meaning of volume of distribution, or synonym of this volume of distribution, is apparent volume of distribution, and it is usually qualifying the distribution of a drug between the plasma. Means how the distribution takes place between the plasma and the rest of your body after oral or parenteral dosing. Suppose you are taking a tablet or capsule or any other formulation by the oral route or by the parenteral route. In this, you just check how much drug distributed in your body from particular site to blood to a particular site in plasma or rest of your body. And this is also called as apparent volume because all parts of the body equilibrated with the drug do not have an equal concentration. We already discussed that there's a different equilibrium according to body parts, and according to this, there's a concentration is also varying. All body parts don't have an equilibrium concentration or same amount of drug present. Maybe after distribution or when drug reaches to a systemic circulation with the help of blood, it reaches to various site or various tissue. After reaching this drug to various tissue, there may be chances that your drug it is not in uniform for all site. There may be chances that it is somewhere less or somewhere more, and this is not show equilibrium distribution to all your body, and it is defined as a volume in which the amount of a drug would be uniformly distributed to produce the observed blood circulation. And so you can also say that this volume of distribution is also defined as the amount of a drug, or how much of the drug would be uniformly distributed, or how drug is uniformly distributed to produce the observed blood circulation, or drug reaches to blood circulation at how much concentration available in your blood, So this defined as how much drug present in your blood circulation. And ingress distribution is just opposite to distribution. And with distribution, you can say that highly lipid soluble drug, when given by intravenous route or by inhalation, only initially get distributed to organ with high blood flow. Example: brain, kidney, and the heart, etc. We already discussed that there are certain tissue or organ which have a high perfusion rate. In this, mainly brain, kidney, heart type of organ have a high perfusion rate. And when you take a drug and your drug may be lipid soluble by the IV route, so there may be chances that it get redistributed to the organ or maybe again distributed to that particular organ which have a high blood flow or a high perfusion rate. And those organ or those tissue which have a low flow or a low perfusion rate, in this condition they maybe contain less drug or less concentration of the drug, and drug again and again they distribute to only those drugs which have a high perfusion and blood flow rate. Next is less vascular but more bulky tissue like muscle, fat take up the drug and plasma concentration falls and drug is withdrawn from this side. Some other less vascular or fatty material or muscles like tissue also have a capacity to take the drug from plasma concentration or take the drug at particular site. But this is have less affinity compared to higher perfusion rate or high blood flow rate organ. In the next, if the site of action of the drug was in one of the highly perfused organ, that is redistribution result in termination of a drug action. If you can say that the site of action drug was one of the highly perfused organ and you require effect on suppose heart, in this condition there may be chances that due to high perfusion of blood flow rate, the drug get again and again distributed on the heart, and this redistribution takes place to particular required site to multiple times or multiple drug concentration is present on heart, and due to this greater lipid solubility of drug, faster is the redistribution. Suppose this distribution is for lipophilic drug and it's lipophilic in nature. So in this condition, distribution is faster or absorb more compared to hydrophilic drug due to their lipophilicity in nature. This is a diagram of the real volume of distribution according to logically millimeter to the body water. In this, you can see that total water is plasma. It's a very less amount present in your body when you compare overall body. And next is interfacial volume. In interfacial volume, it is a little bit more than plasma, but it's not too much sufficient. And in this next is intracellular volume. It is the largest amount present, that is 42 liters approximate. Larger volume when compare all this above body water, then large is intracellular volume or intracellular fluid only. If you can see that extracellular volume, then extracellular volume is also less compared to intracellular volume. Extracellular volume is only 14 liter is present, but intracellular volume is 42 liter present. There's a too much difference between this intra and extracellular volume. Next is interfacial volume. This interfacial volume is only 10 liter. It is also less than extravascular volume. And next is plasma volume. Plasma volume is very much less compared to any other volume, and it's approximately 4 liter in your total body water. And next is intracellular volume, that is 28 liter, or when you say that it's a more than extracellular volume. This is all about the volume distribution of fluid in your body or total body water. Next is the volume of each these compartment can be determined by use of a specific marker or tracer. There is certain marker or tracer you use. With the help of this marker and tracer, you can easily determine how much drug is distributed, how much volume present to a particular compartment, particular part of the body. And these marker and tracer play very important role for determining volume of the drug or volume of the body fluid. And in this, we can see that this table is very important. In this, first is physiological fluid and compartment site, and in this marker used in appropriate volume in liter. First is the plasma. According to this plasma compartment, marker used is Ivan blue and European green. These are the markers mainly used to check the body fluid or body water contained in plasma. And approximate volume of this plasma is mainly observed 4 liter. Next is extravascular tissue. For extravascular tissue compartment, mainly markers used like is inulin, rabinose, and mannitol. These are the 3 markers used for extravascular fluid. And approximately volume in liter is 14 liter for extravascular fluid. And total body water, you can check total body water with the help of these 2 markers, D2O and antiviral. These 2 markers are used mainly for check how much drug, not drug, but how much body water is present or total body water present. And volume of this total body water is approximately 42 liters. So these are the markers that are used for determining body water or particular compartment water. With the help of this marker, you can check this is sufficient or not according to this specific unit. Or this is standard liter volume. And in this, intracellular fluid volume can be determined as a difference between the total body water and extracellular fluid. Means you see that these are the compartment fluid present. In this, if required to check intracellular fluid volume, in this you easily check this intracellular fluid volume with the help of total body water and extracellular fluid. You just minus this total body water with extracellular fluid. If you minus this total body water with extracellular fluid, it gives it intracellular fluid, because both intracellular fluid and extracellular fluid form the total body water. That's why if you calculate extracellular fluid and only total body water, then no need to calculate individually intracellular fluid. With the help of this extracellular fluid and body water, you can easily get the readings of intracellular fluid. Just minus the total body water with extracellular fluid, and the value of intracellular fluid. Next is the drug which binds selectively to plasma protein. In this example, warfarin have apparent volume of distribution smaller than the real volume of the distribution. Means how much drug is bind with plasma protein, or which binding site is responsible. In this, warfarin have a more apparent volume of distribution or smaller than the real volume of distribution. And the VD or volume of distribution drug lies between the blood volume and total body water. And in this, 6 to 42 liter body water is present approximately. Means volume of distribution, you can say that it's a blood volume and a total body water both. And the readings of this volume of distribution lies between the 6 to 42 liter. And in this volume of distribution, you can say that drug which binds selectively to extravascular tissue. In this example is chloroquine, and chloroquine is an anti-malarial drug and have apparent volume of distribution larger than the real volume of distribution. This apparent volume of the chloroquine show more value or large value for distribution compared to when the real volume of the distribution. And next is the volume of distribution. Such drug is always greater than 42 liter. This is reading should be above 42 or greater than 42 liter. Next is difference in drug distribution among the various tissue arise with a number of factors. These are the factors that is responsible. In this tissue permeability of a drug, how much drug is permeable to that particular tissue or particular site. In this first is physicochemical property of a drug like molecular weight, size, pK, partition coefficient, physiological barrier to diffusion of the drug. Means not only physiological factor, only size, particle or molecular size or pK, pH or partition coefficient is not sufficient for this tissue permeability. But it may be varied depending on the size or depending on the nature of the particular drug. Or certain types of barrier. We already discussed different barriers. This barrier is also play important role for the distribution of the drug, crossing of the drug to particular barrier site. Next is organ tissue size and perfusion rate binding of the drug to tissue compartment. How much drug is bind to particular tissue or particular organ, and this binding is also depending on the type of the organ or affinity of that particular organ towards that drug. And in this, blood component extravascular tissue protein include. Next is miscellaneous factor. miscellaneous factor, we covered age, pregnancy, obesity, diet, disease state, and drug interaction. Means this distribution is also depend on the age. If a person don't absorb their body parts completely, in case of the children, the distribution is also less or may have a high affinity to certain tissue due to thick membrane, or in pregnancy, the drug distribution is also may vary because in this the placental barrier is very thin, and larger particle size also can cause this barrier or show some toxicity like teratogenicity type toxicity. Obesity is also shows some distribution problem or show fast distribution of lipophilic drug due to fatty material present in obese person. And diet in this may be fasting state or food that we take is also responsible for different distribution amount of the drug. Disease state, if person is suffering from certain disease or taking some another drug for that particular disease. In this condition also distribution is vary because maybe chances that drug-drug interaction is takes place, or maybe that particular disease don't distribute the drug that particular site. So there is the miscellaneous factor. This are mainly arise to distribution problem. Next is the significance of a protein binding of the drug. In significance of protein of binding of the drug, this first is absorption. The binding of absorbed drug to plasma protein decrease free drug concentration and distribute equilibrium. Mean absorption takes place to plasma protein or with the help of plasma protein, but plasma protein is decreased due to free concentration or distribution of concentration is decreased or equilibrium is achieved. And this condition and concentration gradient are established, which now act as a driving force of further absorption. And this remaining concentration or same condition may be act as a driving force of further absorption. Drug is available for this absorption. Next significance is systemic solubility of the drug. How much drug systemically soluble to that particular body or particular site. In this water insoluble drug like neutral endogenous macromolecules like heparin, steroids, and other soluble vitamins are circulated and distributed to tissue by binding specific lipoprotein and acts as a barrier for drug hydrophobic compound. Means in this you can say that this systemic solubility is mainly depend on the type of the drug. It's a hydrophilic in nature or maybe lipophilic in nature. Suppose a drug in a neutral in nature or endogenous molecule, and it's a water insoluble drug, means it's a lipophilic in nature. In this you can take example like heparin, steroids, and other oil soluble vitamins. You can take these are the hydrophilic in nature, and the distribution or solubility of this drug is more compared to your hydrophobic drug or hydrophilic drug than any other compound. And next is distribution. The distribution of plasma protein binding, those favor the uniform distribution of drug throughout the body by buffer function. A protein bound drug is particularly does not cross the blood-brain barrier and placental barrier and glomerulus. Means for distribution, and the drug distribution may be vary according to type of the drug, or maybe this is depend on the which barrier cross, or that particular drug is cross that barrier or not. Suppose in case of blood-brain barrier, it's a certain problem to cross this barrier, but in placental barrier, all drugs are easily cross this placental barrier, and if this distribution and absorption is not affected, then maybe chances that drug is excreted out, and due to this excretion, then there is chances that desired effect or therapeutic effect is not observed in that particular site. Next is tissue binding, apparent volume of distribution, and drug storage. How we calculate this apparent volume of distribution and tissue binding takes place. In this, a drug that bind to blood component remains combined to blood have a small volume of distribution. Those drugs who bind with blood component or blood cell, and those who bind with blood component have a small volume of distribution and show small or less volume of distribution. And next, in this drug show extravascular tissue binding have a large volume of distribution. If drug are bind with extravascular tissue, it show more volume or large volume of distribution. And you can say that when your drug is bind with blood component, it shows less distribution, but drug is bind with extravascular tissue or highly perfused tissue, it shows more distribution or large distribution. And the relationship between this tissue drug binding and apparent volume of distribution is calculated with the formula. This is the formula. VD is the volume of distribution, and X by C, where X by C, X is the amount of drug in the body, or concentration of drug in your body, and C is the plasma drug concentration. You calculate this volume of distribution by the help of this formula, and in this you can say the amount of drug in your body is equals to, or X is equals to VD into C. You just interchange with this, and due to this, X is equals to VD into C, and a similar amount of drug plasma it calculate with the help of VP into C. Means instead of volume of distribution in your body, you just replace the distribution into plasma, and when you're checking this drug in plasma, that's why writing VP into C. And amount of drug in extravascular tissue, you just write VT into CT. Means a total amount or total concentration in extravascular site or extravascular tissue. These are the formula. You calculate with the help of this formula how much drug is distributed to a particular site or a particular organ, maybe in your body, or maybe extravascular tissue or intravascular tissue, or maybe in a plasma. The total amount of a drug in your body is VD into C is equals to DP into C plus VT into CT. Means volume of distribution in your body you calculate, and that it is present in your extravascular tissue or maybe in the plasma. It's a sum of volume present in the plasma or extravascular tissue. This is formula for total body distribution, VT into C, and VT is the volume of the plasma, and VT is the volume of drug in extravascular tissue, and CT is the tissue drug concentration. So with the help of this formula, you easily calculate how much drug distributed in your body. And you can write this formula in this way, like VD is equals to VP. VP is the volume present in your plasma. VT plus, in this VT is the volume of drug in extravascular tissue into CT divided by C. The CT is a tissue drug concentration, C is the concentration, and you can divide both sides by C in the above equation. When you divide by C equation, then you calculate the fraction of unbound drug in the plasma, that is FU. FU means fraction of the unbound drug in plasma, and FU calculate with the help of this formula. In this, you write that concentration of unbound drug in plasma divided by total plasma drug concentration, FUT is equals to CUT divided by CT. It's the formula for fraction of unbound drug present in your plasma. And next is assuming that equilibrium unbound or free drug in plasma and tissue is equals to CT is equals to FU, and you can maybe interchange this reaction. In this, when you change C is equals to FUT, we arrange this volume of distribution formula. We can write VP, volume distribution in plasma, plus VP into FU, and divided by FUT. Because in this you can say that here we write CT. Instead of CT we write FU, because we replace FU to CT. Because CT is equals to FU, and instead of C, here is the C in volume of distribution formula. So we can replace this FUT, because C is equals to FUT. That's why we replace CUT into FUT. And substituting the above value in equation 1, that is previous one equation, it is clear that greater the unbound or free concentration of the drug in plasma, larger its volume of distribution. If more unbound or free drug is available in the body and present in your body, there may be chances that larger concentration of free drug or larger volume of distribution takes place. In condition of unbound or free drug concentration. Means you can say that in your body large amount of free concentration of free drug or unbound form of the drug is available. In this condition, larger the volume of distribution takes place. Next is displacement, interaction, and toxicity. This is a table for this displacement, interaction, and toxicity. In this person drug before displacement, in this first is bound drug. There's two drugs for this person before displacement. In this, maybe calculate person drug before displacement or person drug after displacement. Means difference between before and after displacement. This is a bound drug, and there's a two example of a drug, drug A and drug B. In case of before displacement, drug A is 91% and drug B is 90%. And in another free form, it's a drug A is only 1% and drug B is only 10%. Means more drug bound is observed in before displacement. That is, A drug is 99% and B drug is 90%, and free drug is only 1% in A and drug B for 10%. And next is percent drug after displacement. In this, we calculate that two drug A and drug B. In this bound drug A is 98% and drug B is 89%. And there's a free drug is also very less, that is 2% is drug A and for drug B is 11% free drug after displacement. With the help of this, you can calculate percent drug increase in free drug concentration is 100% in A and 10% in drug B. And the example is like Kinetics DI delivery of NSAID drug, displacement of digoxin by quinidine, displacement of warfarin by phenobutazone. These are the example. If this type of drug takes place, displacement interaction. So it's an example of this displacement reaction. Interaction is significant if drug bind more than 95%. You can say that this interaction may be significant if your drug get bind with 90% or at least up to 90%. Next is kinetic of protein drug binding. In this kinetic of a protein drug binding, the kinetic of reversible drug protein binding for protein with one simple binding site can be described by law of mass action, and this is the formula for this law of mass action. Protein plus drug and is equals to drug protein complex. Means your drug get react or bind with protein, and when bind with protein, it forms the drug protein complex, and you can write down this P is equals to protein and D is the drug and form the complex, that is PD, protein drug complex. And the law of mass action, or according to law of mass action, associated constant Ka can be expressed as a ratio of the molar concentration of the product and molar concentration of the reactant. This equation is by one binding site per protein molecule. Means you can simplify this equation, or you can express this equation by the help of this formula. It's a formula that explains that molar concentration of the particular product or constituent of that particular product is depend on the ratio, whether how much product or how much concentration of reactant is present, it's a product, and concentration of reactant is P and D. And in this formula is mainly dependent to assume one binding site per protein molecule. Next is experimentally both free drug, that is T, and protein bound drug PD, as well total protein concentration P plus PD, and may be defined to study the binding favors of the drug and determine ratio, that is R, defined as following equation. That is R is equals to moles of the drug bound divided by total mole of the protein. Is how much drug bind or bound with protein, or how much total mole of protein is available for binding. Next is mole of drug bound is PD, and total mole of protein is P plus PD. And this equation you can write or maybe change. R is equals to PD divided by PD plus P. This is a modified equation of this R. And substituting this value of PD from equation number 2, that is previous one equation, and after substituting this PD to equation 2, we get R is equals to Ka P into D divided by Ka P into D plus P. You simplify this fourth equation and convert into R is equals to Kab divided by 1 plus K into D. This above equation of fourth equation describes that the simplest solution in which one mole of a drug binds to 1 mole of a protein. Means binding of a drug to protein is similar, or is 1:1 ratio. Means 1 mole of a protein is bound with 1 mole of a drug, and it forms 1:1 complex. In case of assume that only one independent binding site for each molecule of a drug, if they are an identical independent binding site per protein molecule, then following is used. R is equals to Nka into D divided by 1 plus Ka into D is the equation of fifth number equation. In terms of Kd, which is 1 divided by Ka, or equation 6, reduce or maybe converted into this. R is equals to Nd divided by Kd plus D, and these protein molecules are quite larger compared to other drug molecules or maybe more than one type of a binding site of the drug. If there's any one type of the drug site bind independently on each binding site with its own association constant, then equation, this sixth equation or this equation may be expanded into seventh number, and you can write this like this type: R is equals to N1 K1 into P divided by 1 plus K1 into D plus N2 K2 into P divided by 1 plus K2 into D, or maybe you plus this number of binding to protein or drug to protein. And in this value of association constant and number of binding site are obtained by various graphic method. There are different graphic methods used to represent this equation. In this, there's a certain graph. Mainly, this is the first graph for direct plot, and the second is double reciprocal plot. And the first plot, you can say that it is matrix plotting R versus D. In this free drug concentration, this is the D, or drug concentration, free drug concentration versus moles of the drug bound per mole of the protein, or how much protein bound that particular free drug concentration. In this, you can say that this graph is increase or this reaches at the saturation point or equilibrium condition. After this saturation of binding site, you see that there's a higher concentration or more concentration of binding takes place in this direct plot. This indirect plot will directly check how much drug bind with particular protein by the help of direct plot. And a second is double reciprocal plot. In double reciprocal plot, we can plot this with the help of last equation or with the help of equation number 6. And this is number 6th equation. 1 divided by is equals to 1 plus Ka into D divided by Nk into D. 1R is equals to 1 divided by N into Ka into D plus 1 divided by N. This is the equation. With the help of this equation, you can calculate double reciprocal plot or plot the double reciprocal plot. In this, it's a graph of double reciprocal plot, a graph of 1 divided by R versus 1 divided by D. This is 1 divided by D divided by 1 R, and this is known as double reciprocal plot. In this, you can say that increased amount of concentration binding takes place, and the slope is observed. In this slope, show equation that is 1 divided by Nk0. From this graph, the number of binding sites may be determined. That is, by intercept and association constant may be determined. The slope value of N is known. In this condition, for determination, you at least know about N value, or N value should be in a known condition. Next is scattered plot. And in this scattered plot is a third graph that is determining kinetics or binding of the protein. In this scattered plot, which is arrangement of 6th equation, and the scattered plot spread the data to give the better line of estimation of binding constant and binding site from the equation 6. And this is all about scattered plot. And these are the 3 plots which is used for calculating the protein binding. And after this completion, this lecture or this PPT, you should know about basic outcome, and these are the outcomes which you should know after this complete topic. And this is, I think, last topic of first unit. And in this, we know about the introduction of the kinetic required for drug distribution. Yes, which kinetic is required for drug distribution, volume of distribution. Or certain derivatives. In significance of drug distribution, in significant we see that absorption part, solubility part, and distribution part is how the significance is responsible for protein binding as well as distribution process. And kinetics, including graph, we see 3 types of graph: direct plot, scattered plot, or double reciprocal plot. So you know about the difference between these 3 graph or 3 plot. With the help of these 3 plot, you can calculate the kinetics of this binding. And you can also know that how you plot this graph, or which axis you plot which value versus this value, and the distribution of the drug, how the distribution takes place, is this for all drug or not, and how you calculate this distribution, or how you check that this distribution takes place that particular organ or tissue. So this is all about outcome of this complete topic. the reference part for this kinetics and significance. First is Brahmankar, D.M. Jaiswal, SP Biopharmaceutical and Pharmacokinetics. University, second edition, Prakashan. Second is Tiffany's HP Bajaj, a principle and application of biopharmaceutics and pharmacokinetics. First edition, Carrier publication. Third reference is Sargent L. Vox, Adrug, BCU, applied biopharmaceutics and pharmacokinetics. Fifth edition, MCU, Hell Company. Fourth reference is Tiffany's HP Nagasakar MS, Introduction to Biopharmaceutics and Pharmacokinetics. First edition, Nirali Prakashan. And fifth reference is Kodarkar A. Bakriwal S. Biopharmaceutical and Pharmacokinetics, second edition, Nirali Prakashan. Sixth is Madan P.L. Biopharmaceutics and Pharmacokinetics, first edition, JP Brother Medical Publisher Limited. And seventh edition is Kwati KD, Essential of Medical Pharmacology. Sixth edition, JP Brother Medical Publisher Limited. And eighth reference is Baba FSK, Essential of Pharmacotherapeutics. Fifth edition, S. Chand and Company Limited. This is all are the good books, and you can use any one book or the combination of these books for good matter. These books are sufficient for this topic. After this reference part, we include question part, and in this question, you solve all questions. After completing this topic, you easily answer this question if you know complete information of this topic. And this question part, first question is which theory of distribution is known as limited solvation rate theory? A is surface renewal theory, B is diffusion layer model, C is Hixon Crowell model, D is interfacial barrier model. Second question is therapeutic equivalent drug do not have a. The option is same dose strength, B is same safety profile, C is same clinical effect, and D is they have a pharmacological equivalent. In third question, when K is kept constant for smaller Ka value, then there will be effect on A to C. The option is increase, the option is decrease, and C option is no change, and D is all main chain, that is ABC option. And in fourth question, identify the incorrect statement regarding the ionized drug molecule. And this you check which statement is correct, incorrect, or wrong out of this ABCD option regarding ionized form of the drug. And this A option is lipid insoluble, B is rapidly passed across the placenta, C option is poorly crossed blood, and D is easily excreted. And it's so fifth question, identify the correct order. In this, A option is absorption, followed by metabolism, then distribution and excretion. B option is distribution, metabolism, absorption, and excretion. And C option, absorption, followed by distribution, then metabolism, then excretion. And D option, absorption, excretion, metabolism, and distribution. And in sixth question, paddle over disc apparatus is extensively used for evaluation of the A option tablet, and B option is capsule. C option is transdermal drug delivery system, and D option is all type of the formulation. These are the questions regarding specific evaluation of dissolution test. In seventh question, the drug that demonstrates saturation kinetics show. A option is elimination of the drug, follow first order kinetics. B option is elimination of drug, does not follow first order kinetics. And C option is elimination, half-life does not change as dose is increased. And D option is elimination of drug follows zero order kinetics. In seventh question, you know about what is saturation kinetic, and according to saturation kinetic, you can correct or select one option out of this ABC, which one is correct. And eighth question, the elimination of drug by saturable enzyme process described by A is Michael-Menten equation, B is Michaelis-Thomas kinetics, C is Michaelis-Henderson kinetics, and D is Michaelis-Siverson kinetics. These are the four options for eighth question. And in ninth one, what is pharmacokinetic or definition of a pharmacokinetic? You know about pharmacodynamic and pharmacokinetic parameter. So if you know all these parameters, so you can easily answer this ninth question and select any one correct option out of ABCD. In this A option, the study of biological and therapeutic effect of the drug. B option is the study of absorption, distribution, and metabolism and excretion of the drug. C option is the study of mechanism of the drug action. And D option is the study of method of a new drug development. This is all four option ABCD, and out of this four option ABCD, you select any one correct option which fit the pharmacokinetic parameter or related to pharmacokinetic parameter. Next, then the last question, 10th question. This is also include pharmacokinetic related information. In this, what does pharmacokinetic include? Means what parameter you should include in pharmacokinetic, or pharmacokinetic include which parameter. In this, A is complication of drug therapy, B is influence of drug on metabolism process, and C is drug biotransformation in the organism, and D is influence of the drug on gene. These are the 4 options. Out of this 4 option, or out of this ABCD option, you select any one option which is correct or which is fit for pharmacokinetic parameter. This is all about pharmacokinetic, or maybe regarding this particular topic, kinetic and significance. And you can answer this question after completing this lecture. So thank you so much for listening and watching this video. Thank you so much, everyone.